Got it? All right, I'll begin. Heavenly Father, we thank you for this morning. Thank you again, Lord, for these students. Just pray that you help us to use this time wisely, just to try to understand a little bit more about sequences and also any questions that remain about the homework on differential equations. Lord, in your name I pray. Amen. So guys, you got questions? Actually, before you have questions, let me just talk about a couple problems, then I'll erase them. All right? So I'll be brief. These are relevant, of course, to your homework. So there's kind of two things at play here, right? And so what I told the earlier section is I need some way of communicating two different goals, all right, in as much as sequences are concerned. The one goal I have is just sort of a crude goal. Given a sequence, does it converge or diverge, and what does it converge to? Just yes, no, what does it converge to, all right? So basically I'm setting aside the question of justification. Just how do you actually figure out what the case is, right? So what are some sort of, techniques to figure out, to answer those kinds of questions? That's the first question. That's the one we all have to struggle with to start with. And once you've settled that, once you've decided just basically on intuition or some sort of informal calculation, it diverges or it converges, then the next level up, right, is justification. How do you justify the sequence converges or diverges? Justification, right, is going to involve the use of theorems, calculus, inequalities, right? Things which are already known. So like for the purposes of your homework, we can assume this is already known, all right? Now I haven't proved this yet, but I will prove it, maybe tomorrow, I don't know, sometime soon. The limit as n goes to infinity is infinity if p is greater than 0, it's 1 if p is equal to 0, and it's 0 if p is less than 0. So we take these truths to be self-evident, all right? We use those to justify other things, okay? So what I have underlined in green here is not justification. This is intuition, right? If you go watch the Khan Academy, he's probably just going to talk about intuition, right? He's not a mathematician. He wouldn't know what justification means. It's fine. It's great. But that's the starting point. Not an ending point, a starting point. So this example, number 16, I'm looking at 10 to the 10th root n over n plus 1. All right. So I'm like, well, what is that? This n plus 1 is cluttering things. If I think about n being a million or a kabillion or, network of Trump, national debt, whatever big number you want, something huge, then this becomes n, right? Because that's really just n. And if you look at that, well, that's really just 10 to the 10th over root n by algebra, right? So intuitively speaking, this is nothing more than 10 to the 10th, which is a constant, a huge constant. Sorry, huge constant, but still just a constant over root n. And so that goes to 0 by this fundamental truth. That's how I find that the limit converges and goes to 0. That is not a justification. It's an impartial justification. So if I ask you to find if the sequence converges or diverges, right, and if so, find its limit, basically what I'm telling you there is I'm just grading your answer. Okay? However, if I say, that means no partial credits available too, by the way. Sorry. If I say justify, on the other hand, then I'm expecting you to do that and to explain why in terms of more basic truths, in terms of theorems. All right? So for this one, we can use the Squeeze Theorem, you see, because 0 is less than this, that's clear. And then this is less than that, right, because I made the denominator larger. So that's the way inequality works, right? But this by algebra is just that, okay? The limit of the constant sequence is 0. I think I proved that for you guys yesterday. And I mean, the limit of constant is just the constant again, right? We chose n equals to 2. You make it, whatever. So that we know. And then the limit of this, well, I can pull the constant out, right? It's huge, but it's still just a constant. It pulls out, and then we're back to the p equals to minus 1/2 case. So it goes to 0. And so I have a sequence above and a sequence below and a sequence above both going to 0. Hence, this also goes to 0 by the Squeeze theorem. That is a justification that the limit converges to 0. See the difference between that and what I have up here in green? Right? I could easily ask you like a series of like 10 questions and just expect you to find the answer one after the other, like bam, 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 bam. You could do those in like 10 minutes. If I asked you to justify, it's a much more laborious thing, right? You actually have to think through it, give careful arguments, use theorems. All right. Number 18 tilde. It's like number 18 in your homework from section 11.3, all right? So here I'm faced with the natural log of n cubed plus 7 over 2n cubed minus 3. N equals to 1 would be problematic, right? N equals to 1 would give me minus in the denominator, which would not be good, because natural log of a negative number is only defined in Math 331, complex analysis. It's actually imaginary. But anyway, not here. We try to keep it real. So that is positive if n is greater than or equal to 2, right? And then I'm like, aha. You can check out this sequence, right? It's a rational sequence. So I divide by the largest power of n. It breaks it down to 1 plus 7 over n cubed, 2 minus 3 over n cubed. I go back to here again. I've got p less than 0. 1 over n cubed goes to 0. This is a fundamental truth for us at the moment. We hold it to be self-evident that these go to 0. And so that's 1/2. My point is, this sequence converges to 1/2. And it's inside the domain of this continuous function called the natural log. Therefore, I can bring the limit of the log sequence to be the natural log of the limit of the rational sequence. See? I can bring the limit inside because of the theorem we proved last time. Over here somewhere, I forget where we proved it. Anyway, we proved it last time. It was theorem 11.3.12, if I recall correctly. So therefore, you know. Now, I don't require you to name that theorem by name because it's got a rather boring name. Theorem 11.3.12. Not that exciting really, or 3.2, I forget. See, I already forgot. I will know in my heart if you understand the theorem or not by whether or not you check to see if the theorem should be used. How do I know if you're using the theorem correctly or not? It's pretty simple. You tell me that I've got a function which is continuous. You tell me that the sequence meets the condition which is needed to put it into the function, in this case that it's greater than 0, right? If you've done those two things and then you write this, I can justly infer that you know the theorem and are using it. That's not optimal. It'd be better if you called the theorem by name, but since we don't have a good name for it, I'm willing to look the other way, since we can't do proper name calling on this theorem. Do you guys want to give it a name? I mean, we could give it a name. The Pac-Man Theorem? Let it be such. We use Pac-Man too much. That is true. We need something else for it. You do have a, what's that? It's the Miss Pac-Man Theorem? Miss Space Invader Theorem? It should be at least somewhat appropriate to the theorem. I mean, it's involving yeah. It's crazy as anything else. I'll call it the Space Invader Theorem. There you go. Although I think at this point we'd all prefer to just say theorem 11.3.12 or 2 or whatever it was. Is it 12 or 2? I can't remember. Try not to shoot you with, it's 12. It's on page 544. All right, anyway, name calling aside, I hope you get my point. Number 63, and then I'll take your questions. I did not assign, but I've assigned ones close to it and like it. Here we have a recursively defined sequence that's starting at 1, and then it's defined to be a sub n plus 1 is 1 over n plus 1 times a sub n. We're asked, does it converge, does it diverge? If it does converge, find its limit. So Oh man, I buried the lead earlier. Just realized. So if you look at this, right? A sub 1 is 1. A sub 2 is 1 over 2 times 1, because that's the rule. Then I got 1 over 3 times that, because that's the rule. And then, well, if you look at the pattern, it's pretty clear what it is. Right? It's 1 over n factorial. So what do we got? We've got a sequence of positive terms. This is bounded below by 0. Right? And it is, as you can see, the ratio of an plus 1 to an is equal to 1 over n plus 1, which is less than 1. That means it's what? Decreasing. So we have a decreasing sequence bounded below. Therefore, by the bounded monotonic sequence theorem, we know it converges to its greatest lower bound, in fact. Its greatest lower bound is, in fact, 0 here. So the limit of the sequence is 0. Now, but how to prove something's the greatest lower bound? See, that's kind of a, that's not that easy. So rather than, I just say that I know the limit exists and is the greatest lower bound by the monotonic sequence theorem. To actually prove it's 0, a squeeze theorem argument is the way to go. See, because you got 0 is less than 1 over n factorial, right? But if you think about it, n factorial is what? So this number here is what? It's something that's either 1 or 2 or 3, or it's certainly larger than 1, right? So if I replace that with 1, I've made the numerator and the denominator what? I've made the denominator smaller if I replace it with n, right? I'm just saying, is n smaller than n factorial? Yes. Certainly. So then this fraction is larger. But by the squeeze theorem, this goes to, not by the squeeze theorem, by just common sense and this guy. 0 goes to 0, and 1 over n goes to 0. Therefore, by the squeeze theorem, 1 over n factorial goes to 0 as well. Now, that said, you guys, I probably wouldn't complain much if you didn't give me an argument for 1 over n factorial going to 0. If you say 1 over n factorial goes to 0 as n goes to infinity, by common sense, I'd be hard-pressed to argue with you there. So I think the squeeze theorem argument is kind of not entirely necessary here. On the other hand, this one, there's some kind of funny stuff going on, and so, it's good to have an argument. Certainly, it won't be too long where I would hope that you just look at 1 over n factorial and go, wait a minute, that's going to 0, clearly. On the flip side of things, of course, I could ask you to prove that carefully, and then squeeze theorem would be a great tool to use. Any questions about these? I'm going to erase and then take your other questions. I'm pretty happy with this trifecta of examples. It gives you a pretty broad picture of techniques in 11.3. Rational sequence stuff, the squeeze theorem, and the composite function. Composite function theorem. That's what it is. It's the composite function theorem. You're composing a sequence with a continuous function, right? So you guys got questions? I view the torus problem like a canary in the coal mine of your grades. It tells me something is wrong. Nobody got the torus problem on the test. Not cool, you guys. Not cool. This was a homework problem. It was a homework problem which we worked out together, if I recall correctly. I wrote a solution for you guys. Yes, it may have been a while since you worked it. I understand the mechanics of why exactly you didn't get it. I think many of you A non-trivial portion of you are capable of getting that question right. Absolutely. I don't think it's a statement about your capability. I think you're totally capable. So there must be something wrong with your studying. Time? Yeah. Time would explain a few people not getting it, but not everybody. I'd like to blame time. I just don't think I can. Anyway, I'm going to start having quizzes in here. I think it is needed. So you can expect an announcement about that. Probably starting tomorrow, we'll have a quiz about something. Let's see here. I'll try to be more specific when I make an announcement, but probably the quiz tomorrow will be about sequences. What's the definition of a sequence? Probably the quiz. All right. Anyway, it concerns me nobody got that problem. That suggests to me that there's not enough studying going on. Or you're studying the wrong way. I'm not sure which. Dr. Wang claims that everyone's getting dumber because of smartphones. I don't know. I mean, it is true. I don't think the larger educational circumstances changed a lot since I started teaching, you know? So what would the difference be between students, say, 5 years ago and students this year? I guess it's fair to say the main difference is smartphones, their ubiquity, their use. Surely there's 3 of you who checked a text message in the last 10 minutes I've been talking. Right? Someone in here. Studies have shown that it decreases your learning. Anyway, you guys had questions. Let me not rant. I just want you guys to learn, that's all. So you guys have a question? Yes, sir. Ah, yes, my favorite. I miss section 9.3. Those are simpler times. Don't you think? So here we're faced with y prime prime minus omega squared y equals to 0. Right? And you're supposed to show that the general solution is given by Cauchys and Cinches. So the way to work this problem is the same way we work problem 28, which comes just after it, which is you just go through and write down from our general technique the solution. Remember we had that 3-step recipe thing over here basically and 3 cases. So which case is this? Well, we're given that omega is a positive constant. So I've got lambda squared minus omega squared, which is lambda minus omega, times lambda plus omega equals to 0. And so our solutions are what? Lambda 1 is omega, right? And lambda 2 is minus omega. So then I go to the general, our theorem. Our theorem said what? Our theorem said, I call it the recipe in my older inferior Microsoft Word-based notes. Y is equal to like C1 e to the omega, that's a comma, e to the omega x plus C2 e to the minus omega x. That's the general solution, right? You're like, but the answer says that you can write it in terms of Cauchys and Cinches, right? So how do you get to that? So you're like, but there's an identity, e to the theta is cosh theta plus sinh theta, right? And e to the minus theta is cosh theta minus sinh theta because sinh is odd. You pull the minus out, but cosh is even. So basically, you can just use those identities to take these guys, right, and expand them into sums of coshes and cinches are a difference of cosh and cinch. Let me just use a different, I mean, C1 and C2, these are just labels, right? Without loss of generality, you could say that this is B1 and this is B2, just to give it a different name, right? And you're supposed to somehow show that this is equal to like C1 cosh of omega x, right? Plus C2 sinh of omega x. So how do you do that? I mean, C1 and C2, these are just notations for an arbitrary constant, right? But B1 and B2 are just arbitrary constants. So if you just a matter of relabeling things, basically. Like, for example, you get a cosh and a cosh, and cosh and a cosh. So like C1, I think, in my current notation, is just B1 plus B2, right? So you just let B1 plus B2 be C1. What would C2 be? Anyway, if I write any more, I've solved the problem, but that's how you do it. Yes, sir?
You can solve it by just replacing y with cosh and sinh, and then find y prime prime, and then just replace it.
I guess that would be fair. You could just show that cosh and sinh are solutions and take an arbitrary linear combination of them to get the general solution. That kind of begs the question of how you know that cosh and sinh form a fundamental solution set, right? But that's the part of differential equations I'm not testing you guys on. So the deficiency in your solution, I would find acceptable given the parameters of ignorance which I've set in this course. I mean, like, I'm allowing us to be not careful about what it constitutes a solution set. I'm leaving that for differential equations. In particular, you guys can skip problem 29, which is something about Wronskians. I assigned this problem when I made the homework set because it looked very interesting. And Wronskians are very interesting. To complete the story here, we really should talk about them. But, you know, then I started teaching this course and kind of saw where you guys are. And I said, well, there's some battles worth fighting, some battles not worth fighting. So I set that one aside. I'm sorry I didn't tell you earlier you could skip that problem. If you have worked it, good for you. You're smarter for it. But anyway, I free you of the obligation to read and study about the Wronskian if you haven't already, okay? Yep.
So what I did was replacing y with C1 cosh omega x plus C2 sinh omega x, and then I find y prime prime.
Yeah.
And then I plug into that. And
That is totally fine solution as well. Yep. You see, the advantage of my solution is just that if I have given you that this is the general solution, what I'm arguing here is you can reformulate that thing into what you're given. And so the advantage of my argument is that if you already know that that's the general solution, it follows that the cosh sinh thing is also the general solution. I'll shut up about it. Other questions? 34. See, I thought I talked about this another day, but I'll talk about it again. Y prime prime plus ay prime plus by equals to 0. And where a and b are positive, is it? Is that right? Y of x goes to 0 as x goes to infinity for all solutions, it says. We're supposed to show that, right? Okay, so what does that mean? I mean, what are all solutions here? What are the cases? How do you figure that out? There are 3 cases, right, in principle. You've either got distinct real solutions, repeated real solutions, or complex solutions to the characteristic equation. So the characteristic equation here, lambda squared plus a lambda plus b equals to 0, involves arbitrary constants, right? A and B. So you have to solve it in this way. How do we solve a quadratic equation? We complete the square. So I have lambda plus a over 2 squared plus b minus a squared over 4 equals to 0. So of course I get lambda plus a over 2 squared is equal to what? A squared minus 4b over 4, which gives me what? Lambda is equal to minus a plus or minus the square root of a squared minus 4b divided by 2, right? Yeah, this should look very familiar, yes. This, of course, is the quadratic formula. So analyze it, right? What are the cases possible here? Yeah, all three cases it looks like are possible, right? So case 1 would just be, lambda 1, lambda 2. Well, let's say lambda 1 minus a plus the square root of a squared minus 4b. So case 1 would be a squared minus 4b greater than 0. Case 2 would be a squared minus 4b equals to 0. Case 3 would be a squared minus 4b less than 0.
Over 4?
Oh, 2. Thank you. Yeah, but well, okay, fine. Yeah, 2. Sorry. Yeah, 2. That's lambda 1 and lambda 2, and lambda in the third case, lambda is equal to minus a over 2 plus or minus I over 2 square root of 4b minus a squared. All right. So you just write down the general solution in each one of these cases, and you can argue those things go to 0. What do you need to know to do that? You need to know that when our fundamental truth basically is that if I have e to the alpha x, right? This goes to 0 as x goes to infinity. In what case? If alpha is less than 0, right? But look at it. Well, this one's clearly less than 0, right? Why is the first one less than 0? You might worry that the plus makes it positive, right? But check it out. The square root of a squared minus 4b is clearly less in magnitude than a, because you're taking away something from a squared. So this is negative. So we have a linear, we have c1 e to the minus exponential plus c2 e to a minus exponential. Those go to 0. I guess here you might worry, like you've got y1 is e to the minus a over 2x, and you got y2 is x e to the minus a over 2x, right? That's a little concerning because that's indeterminate type, infinity times 0, right? But now you guys know L'Hopital's rule. Yeah, you can use it. Certainly. Let's see, otherwise it's hard to solve this one. X over e to the a over 2x, right? L'Hopital's rule, infinity over infinity. That's the limit. X over infinity. I think I talked about this some other day, and I just basically said you could assume that this goes to 0. But we can do better than that now, right? Since we know L'Hopital's rule now. That's 0. The exponential wins. The exponential wins. And then this one is like exponentials with negative arguments times sine and cosine. So those also die to 0. There's a lot to this problem, but mostly the hardest part about this problem is writing. I guess there's a certain confidence battle you got to battle. Like, can I really think like this? You know, maybe you have to get over that. But that is what it is. Other questions? I should post the solution to the makeup test here once I get a chance. I was about to this morning, and then, as I mentioned, people actually came to office hours. So, yeah.
11.3, number 58.
Woohoo! Now, I'm curious. One other thing I was meaning to ask you guys about. Show of hands in here. How many people never saw calculation of volumes by shells in Calc 1? There's a few of you. Yeah, I'm starting to think maybe I need to go back and cover that section again. And here it might be good. All right. So 11.3 number. What was it?
58. It's like 2 to the n over n factorial goes to 0 because 2 to the n factorial is less than or equal to 4 over n.
Ah. So the real question you have is, you understand why by the squeeze theorem it would show that if you could establish the inequality. Because 4 over n goes to 0, because it's 4 times 1 over n, and 1 over n goes to 0. So fine.
Getting that inequality.
The inequality, yeah. That's a very good question to ask. Let's see if I can actually say anything cogent about it. I don't know. So we're supposed to show 2 to the n over n factorial. Right, is less than or equal to, what is it?
4 over n.
So this is our goal. Show this. All right, well, see, my mind is warring between two ways of doing this. The one way I'm thinking about is just cluttered, straight calculational. It's probably what you guys want to see. The other way would be by induction, which would probably be a nice solution. I'll try to do both. So 2 to the n, right, over n factorial, what is that? This is 2 times 2 times 2, times 2. N-fold copies of these, right? But on the other hand, we have n times n minus 1 times n minus 2 times times 3 times 2 times 1, right? That's what n factorial is. Is there any kind of like fine print to this? Does it start at n equals to 1 or? So I think then it should be assumed that we're trying to show that this claim is true for all n in the natural numbers. In other words, it makes it an ideal candidate for an induction argument. But I'll behave for a second here, at least. Less than or equal to 4, huh? That makes me think maybe I'm keeping 2 of these, but then doing some kind of sneaky business with the rest of them. Yeah?
Why is the problem like have you specified that it's like less than or equal to 4 over n? Like you could have it equal, like be less than or equal to something a lot simpler and still get the same answer. I don't understand what that means.
I mean, it's either true or false, so we can try to prove it or disprove it.
Yeah. No, just like why did they choose that? Is it just like, let's say like lesser numbers?
I don't know. Nothing comes to mind right offhand. I mean, we'll definitely, as we go on, face this battle again, analyzing factorials with respect to other functions. So I think it's mostly just for the purpose of giving you a specific problem with a factorial that you can try to hone your skill on, mostly that. I can make this, we can play the denominator again, denominator game again, right? How can I make this denominator smaller and thus the fraction larger? How can I make the denominator smaller and consequently the fraction larger? In a way which is maximally lazy. How about everything from 2 and beyond, right? I can trade my n for a what? Two, right? So this is less than or equal to 2 times 2 times 2 times 2 over 2 times 2 times 2 times 1. Let's see, how many factors are here? There are n factors, right? Oh, so I want to keep the n though.
Yeah.
Too greedy. If I chop that out, I've got n minus 1 of these, right? So just keep the n. Keep the n. What's that? Make this a 2 also. Change a 1 to a 2. Oh no, I don't want to do that. I don't want to do that. So the point is, sorry, there are actually how many of these I've done it to? N minus 2, right? Because I'm leaving the 1 alone, I'm leaving the n alone. I'm just making everything in the middle 2, and I can do that to make the fraction larger. And if I do that, I'm sorry, I seem to have solved your homework problem. Can you forgive me? Now that induction argument I gave you. Proof by mathematical induction is very, very useful for problems such as this. So here's how the induction argument goes. N equals to 1 is true, right? Because if I have 2 to the 1 over 1 factorial, that's equal to 2, which is less than or equal to 4 over 1, which, by the way, is 4. So the claim is true. For n equals to 1. Let's do some name calling. Let's call this claim P of n. So P of 1 true. Now assume that P of n is true for some n in the natural numbers. Our goal is to show that n plus 1 is then also true. If you can do this for arbitrary n, then proof by mathematical induction says the claim is true for all natural numbers. So we get to assume that 2 to the n over n factorial is less than or equal to 4 over n. And then I want to consider 2 to the n plus 1 over n plus 1 factorial. What is this? This is equal to 2 times 2 to the n over n plus 1 times n factorial. It's always about the same thinking. Yeah, 2 minutes. Hopefully that's enough. Now, of course, this is less than what? By the induction hypothesis, that's less than 2 times 4 over n plus 1 times n. But of course I can, n plus 1 is some number larger than 1, right? If I change that to 1, it makes the fraction larger, yeah? So this is clearly less than 8 over n. Oh, I should get rid of the n plus 1, rather. I'm thinking the wrong way. I want to keep the n plus 1. I'm trying to show that this is less than or equal to 4 divided by n plus 1. If I can show that this right here, right, is less than 4 over n plus 1, that shows that the claim is true for n plus 1. Do you see how I can trade the n for 1 here? 1 is clearly what? The smallest n can be. So if I replace this with 1, I've made the fraction larger. Well, it could be equals to in the case n equals to 1. Got too greedy. Curses. It's 2 times too big. Man. I should have looked at, so I need to argue that 2 over n is less than or equal to 1. If I have that, then I would get this, right? Is this true? This is interchangeable with 2 is less than or equal to n. Yeah, it's not true for 1. But we already know it's true for n equals to 1, and then we can assume n greater than or equal to 2 without loss of generality. We already know p of 1 is true for separate reasons. So I can assume that n is greater than or equal to 2, and that gets me that. Therefore, Pn plus 1 is true. Therefore, the claim is true for all n. That's argument by induction. Sometimes this is very useful, but I think this is more appropriate to the course, at the moment anyway. I'll give you your test back if you want it. Well, anyway, some of you improved. Some of you stayed the same.